In this lecture, we're on the road again, but we'll be shifting our focus from the work of the highway engineer, who designs the geometric configuration and underlying structural support of major roads, to the work of the traffic engineer, who specializes in facilitating the safe and efficient movement of vehicles and pedestrians within a road system. Now, traffic engineers apply the scientific study of traffic flow to the design of roads, intersections, and traffic control. They're principally responsible for the geometric design of intersections, sidewalks, crosswalks, and bike paths, as well as traffic control markings, signs, and signals. You experience the products of traffic engineering every day, from the overhead sign directing you toward that freeway exit ramp to the timing of the left turn signal at a nearby intersection. Traffic engineers are also extensively involved in conducting investigations to improve traffic safety. These investigations include forensic studies of past crashes to identify potentially hazardous locations and conditions, research on how various physical improvements to roads and intersections can reduce the frequency of crashes, and cost-benefit analyses to establish priorities for future projects that address the most critical safety deficiencies at these hazardous locations. The road and intersection improvement projects currently being implemented in your town are probably the result of such efforts. So what does a scientific theory of traffic flow look like anyway? Well, let's look at one typical example, a theoretical mathematical model governing traffic flow, traffic density, and mean speed. First, the terminology. We encountered the concept of traffic flow last lecture. It's the hourly rate at which vehicles pass a specific point on a highway, measured in vehicles per hour. Density is the number of vehicles traveling on a specific length of highway at a particular instant in time, measured in vehicles per mile. The 6 levels of service that we discussed last lecture are actually defined in terms of traffic density. For example, level of service A corresponds to a very low density of 11 or fewer vehicles per mile per lane, sufficiently sparse to allow unconstrained flow of traffic at high speed. Higher density leads to progressively greater constraints on traffic flow, which corresponds to lower levels of service. And for the purpose of this model, mean speed is defined as the average speed of all vehicles passing a point on a highway within a specified period of time, measured in miles per hour. All three of these quantities are mathematically related by the equation flow equals density times speed. And note that the units in this equation work out consistently, as we would hope. Vehicles per hour equals vehicles per mile times miles per hour. Now, to develop a usable theoretical model of traffic flow, we must also assume a theoretical relationship between any two of these three quantities. One common approach, called the Green-Shields model, assumes a linear relationship between density and mean speed, as shown here. The point where this line intersects the vertical axis represents the maximum speed that's possible on a given highway. And as the graph suggests, this speed can only be attained when the traffic density is extremely low. As density increases, vehicles start constraining each other's movement, and their average speed decreases. You've probably experienced this yourself. You're driving fast on a nearly empty highway, but just as you approach those two slow-moving cars in the right-hand lane, one of them pulls into the left lane to pass the other. Both lanes are now blocked by slower vehicles, and so you have to reduce your own speed until the left lane is clear again. Okay, continuing down the line, greater density continues to cause further speed reductions until the traffic stream comes to a standstill here. This is called the jam density, another condition we've all experienced. Now, based on this theoretical model, we can use the equation flow equals density times speed to derive the corresponding graph of flow versus density, which turns out to be a parabolic curve. Note that at low density, traffic flow is also low. In this region of the curve, the average speed is high, but there just aren't enough vehicles on the road to constitute a substantial flow. Now, as density increases, flow increases, but only to a point. At this critical traffic density, the curve peaks and then begins to drop off. And we've all experienced this phenomenon out on the highway too. Traffic becomes so dense that everyone slows down. Cars in the right-hand lane stack up behind slower vehicles, but they can't change lanes to pass because the left-hand lane is already filled with vehicles. This is called congested flow. And as even more vehicles feed into the flow from on-ramps, increasing density drives down both speed and flow until everything comes to a halt at the jam density. Now, this graph is called the fundamental diagram of traffic flow, and it's a beautiful example of the mathematical approach that underlies traffic engineering. And this theoretical tool has a variety of important practical applications, including rating highways for capacity, predicting traffic jams, and analyzing the adverse effects of traffic disturbances like lane closures. But the aspect of traffic engineering I find most fascinating is intersection design. To a large degree, the performance of our roads is dictated by the intersections, because the volume of traffic that most intersections can handle is less than the capacity of the connected roadways. Most crashes happen at intersections as well. So for these reasons, intersections tend to have a dominant influence on our driving experience, for better or for worse. Now, before we continue, I should explain my use of the word crashes, which is quite deliberate. When two vehicles collide, or when one vehicle leaves the roadway and collides with a tree or a utility pole, you probably call that event an accident. But to a traffic engineer, that event is always called a crash. Indeed, no traffic engineer I know ever uses the word accident, because it seems to describe an event that just happened, accidentally. But the traffic engineer's perspective is that crashes never just happen. They always have a cause, and they're always preventable. Now, back to the place where far too many crashes occur, the intersection. At the most fundamental level, an intersection involves two or more streams of traffic crossing each other, with drivers typically having the option to continue on their present route or to switch from one traffic stream to another. The combined effects of intersecting traffic streams and fallible human drivers making decisions create many possibilities for conflict between vehicles. This simple crossroad at which two-lane roads intersect has precisely 32 conflicts. That is, 32 points at which two vehicles moving in different directions might collide with each other. Thus, every conflict is a potential crash. The principal goals of intersection design, then, are to minimize these conflicts while also facilitating traffic flow, consistent with the physical constraints of the site and available funds. These goals and constraints often conflict with each other, and so every intersection design represents a unique compromise between competing criteria. Intersections come in two flavors: intersections at grade, which have all roads connecting at the same level, and grade-separated intersections, or interchanges, which have routes crossing at two or more different levels. Grade separation invariably eliminates many potential conflicts between vehicles. However, its most common purpose is actually to facilitate unconstrained traffic flow on at least one of the intersecting routes. Now, interchanges can be built in an amazing variety of configurations to accommodate different sorts of traffic requirements and constraints. Let's look at the three interchanges that would be required for the hypothetical highway design we did last lecture. Here's the one at the western edge of the urban area. It's called a diamond interchange, and it's typically used when a freeway intersects with a minor road. Through traffic on the freeway is unconstrained. However, as a minimum, controlled intersections are required where the two freeway off-ramps meet the minor road. Now, if the minor road has low traffic volume, then the traffic control might be as simple as a pair of stop signs. But for our design, the minor road is a heavily traveled 4-lane collector, so we'll need fully signalized intersections with exclusive left turn lanes at both of these locations. Here's a typical example of an actual diamond interchange. A serious disadvantage of this configuration is the possibility of a driver making a wrong turn onto a ramp and entering the freeway in the wrong direction. Well-designed diamond interchanges use signs, pavement markings, and median structures to reduce the probability of such potentially disastrous events. At the east end of our highway is the connection to US Route 39 and State Route 55. Since these are both divided highways, we'll use a full cloverleaf interchange here. The cloverleaf allows unconstrained through traffic on both intersecting routes, while also permitting 8 possible turning movements without stopping. 1, 2, 3, 4, 5, 6, 7, and 8. At the on-ramps, the merging of these vehicles into the main traffic streams is generally controlled only by yield signs. And at the west end, where our highway terminates at Interstate 31, we'll use a variation on the cloverleaf called a trumpet interchange, which works just like a cloverleaf but is much simpler because there's no through traffic on one of the 2 main highways. Thus, rather than 8 possible turning movements, the trumpet only has 4. Now, from a traffic engineering perspective, the cloverleaf interchange has 2 significant shortcomings. And you've probably driven through enough of these things to identify both of them. As we've seen, to facilitate continuous traffic flow, each of the 4 possible 90-degree left turns is actually executed as a 270-degree right turn, like this. These 4 leaves of the cloverleaf must necessarily have a relatively small turning radius, and thus vehicles must reduce speed significantly to negotiate the curve. Lower speed means reduced flow. Moreover, having just decelerated for the tight curve, these same vehicles must now accelerate rapidly for their upcoming merge into the high-speed flow of through traffic. And here's where we encounter the second major shortcoming. These vehicles enter the traffic stream here, just ahead of the exit from the same stream here. As a result, we have significant potential for conflicts between these vehicles, accelerating and merging left, and these vehicles decelerating and diverging to the right. Now, both of these inherent problems have been very effectively addressed in the directional interchange, which is now used wherever possible for the intersection of 2 freeways. The characteristic feature of all directional interchanges is the flyover ramp, which makes a left turn by passing over or under the main freeways. The very large turning radius of these ramps allows vehicles to move from one traffic stream into the other with little or no reduction in speed. The directional interchange also eliminates the conflict between on and off ramps that we saw in the cloverleaf. Note here that the off ramps exiting from the freeway are upstream of the on ramps feeding into the same route. Well, the obvious disadvantage of the directional interchange is cost. Not only do these large radius curves occupy a huge tract of land, but the geometry of the interchange demands that the freeways and ramps occupy at least 4 distinct vertical elevations. We can see them quite clearly in this street-level photo. 1, 2, 3, and 4. And as you can see, a large proportion of any directional interchange consists of multi-span bridges, which also add greatly to its cost. Of course, diamond and cloverleaf interchanges use bridges too, but typically only 1 per interchange, the overpass that carries one stream of through traffic across the other. All of the associated ramps can usually be constructed of earth embankments, which are significantly less expensive than bridges. Clearly, the enhanced efficiency and safety of the directional interchange come with a big price tag. By the way, because all interchanges typically involve at least 1 principal arterial, complex traffic movements, and at least 1 bridge, the design of these facilities invariably requires close coordination between highway engineers, traffic engineers, and structural engineers. We'll examine the sorts of bridges used in these interchanges in the next lecture. The key distinguishing characteristic of our second major category, the intersection at grade, is that an area of road surface is shared by 2 or more roads. Within this area, streams of traffic are able to change from one route to the other at the driver's discretion, greatly increasing the potential for conflicts. Traffic engineers classify at-grade intersections as multi-leg, four-leg, and T intersections. To introduce some of the engineering considerations underlying the design of all three types, let's look at a series of typical four-leg intersections ranging from very simple to very sophisticated. We'll start with this rural crossroad, which might not even have stop signs, relying instead on the two drivers' ability to see each other approaching and adjust their speeds to cross the intersection without conflict. But once the traffic on one route exceeds a certain threshold, stop signs become essential, and the corners of the pavement also need to be rounded off to accommodate the occasional delivery truck or bus turning onto or off of the main east-west road. Here, two local roads from a residential development feed into an east-west collector, and channelization has been added to separate the streams of traffic entering and exiting the local roads. In this situation, channelization has been achieved by these two teardrop-shaped divisional traffic islands, which, in addition to segregating vehicular traffic, also provide refuge for pedestrians crossing these two streets. Now, in this intersection, the channelization is more extensive, providing divisional islands to segregate traffic on all four legs, plus a triangular directional island to guide vehicles turning right from the southbound to the westbound roads. This configuration suggests that the traffic engineer had to accommodate a particularly high volume of traffic along this particular route. And finally, here's a fully developed at-grade intersection that features 4 through-traffic lanes on the main east-west route, exclusive left turn lanes, divisional islands that segregate vehicles waiting to make left turns, right turn lanes, and directional islands to facilitate right turns from the main east-west road without stopping, and merge lanes for vehicles turning right onto the main east-west road. All of these features are designed for improved traffic flow and fewer conflicts, and all would be integrated with signal lights, traffic signs, and pavement markings configured for the same purposes. Now, although the series of intersections we've just seen reflect a huge range of traffic engineering sophistication, it would be a mistake to characterize the simple ones as bad and the complex ones as good. Rather, they all could be superb designs that achieve an appropriate balance between safety, flow, and cost, consistent with the unique conditions on the ground at each location. What factors do traffic engineers consider in designing at-grade intersections? Well, let's address that question in terms of the 6 major elements of intersection design. Element 1, horizontal alignment. Roads should intersect at as close to 90 degrees as possible. Highly acute intersections, like this one, can be problematic because of limitations on visibility, prolonged exposure of vehicles moving diagonally across the main traffic stream, and the difficulty in making this sharp turn, particularly for trucks and buses. Element 2, vertical alignment. If possible, intersections should have gradients less than 3% in all directions, because vehicles approaching an intersection from any direction might need to stop, even when there's no stop sign or light in that direction. And stopping distances can be significantly increased for gradients larger than 3%. Element 3, the radius of curves at the corners of the intersection. Here, the big issue is that the rear wheels of a vehicle don't follow the same track as the front wheels, an inevitable consequence of the front wheel steering systems our automobiles use. Let's use a simple model to illustrate this phenomenon. We'll start by imagining that this simple model represents a 4-wheel passenger car. I'm going to set the steering wheel up front for a right-hand U-turn, and if you watch closely, you'll see that the track of the rear wheels is inside the track of the front wheels. Now let's transform our passenger car into a tractor semi-trailer rig by simply adding a trailer. Once again, I'm going to make that U-turn, and what you'll see is that the effect is far greater as the wheels of the semi-trailer follow a path far inside that of the tractor's front wheels. In fact, when I get to this point, I need to straighten out the wheels in order to drive straight ahead just to get the trailer lined up with the cab again. This phenomenon explains why we often see placards like this one on the rear of tractor trailers. Take heed, that semi-trailer really does take up a lot more of the roadway than you might expect. Because of this phenomenon, the pavement of a well-designed intersection is always extended inside of the traveled lane by an amount that will accommodate the type of vehicles that are expected to use the intersection. This common configuration, called a simple curve with tapers, is shown here with typical dimensions for a passenger car. The dotted line shows the path of the vehicle's front wheels, and the two tapers here provide the required extra space on the inside of the curve. For the sake of comparison, here are the equivalent 90-degree curves for a single unit truck and a tractor trailer, illustrating the dramatic increase in clearance requirements for larger vehicles. Element 4, channelization. As we've seen, channelization is used to reduce conflicts by guiding vehicle movements into well-defined paths, either using raised islands or pavement markings. Specifically, channelization can be used to control the flow of merging, diverging, and crossing traffic streams, segregate traffic movements that will receive different signals, provide storage lanes for turning vehicles, provide refuge for pedestrians, provide a place to mount traffic control devices, prevent prohibited turns, and restrict speed. In general, islands with raised curbs are used in urban areas and areas with large numbers of pedestrians. Pavement markings are preferred in rural areas where fast-moving vehicles are prone to colliding with curbs during periods of limited visibility. In either case, well-designed channelization increases the intersection's capacity, enhances safety, and promotes driver confidence. Element 5, adequate sight distance. At intersections, drivers make decisions about whether to stop, start, accelerate, decelerate, turn, merge, diverge, or just continue at constant speed. Thus, it's incumbent upon the designer to ensure that drivers approaching the intersection from all possible directions have adequate sight distance to make any relevant decision, and then to act upon that decision without risk of collision. The process by which this is accomplished is surprisingly rigorous. To emphasize this point, let's do a simple example. Here's a four-leg intersection with a two-lane local road crossing a four-lane collector with a speed limit of 40 miles per hour. The only traffic control here is a pair of stop signs on the north and southbound local roads. There are actually 12 possible vehicle movements across this intersection, 3 in each direction: east, west, north, and south. And each of these 12 has its own distinct sight distance issues. But for illustrative purposes, we'll consider only one, a northbound vehicle stopped here and intending to drive straight across the intersection and continue northward. First, the distance this vehicle must travel to completely clear the intersection is 10 feet from the stop line to the first east-west traffic lane, plus 58 feet across the intersection, plus the length of the vehicle, which we'll assume to be a passenger car 19 feet long, for a total of 87 feet. Now, using standard statistical data on automobile performance characteristics, we can determine that the average car will take about 6 seconds to travel this 87-foot distance across the intersection. We can also estimate that it'll take the driver about 2 additional seconds to discern whether a westbound vehicle is approaching, decide that there's adequate time to cross the intersection, remove her foot from the brake, and hit the accelerator. Thus, the total time from perception to completion of the crossing maneuver is 8 seconds. During that same period of time, how much distance will a car driving westward at 40 miles per hour cover? Well, distance equals rate times time. So the distance is 40 miles per hour times 8 seconds times the appropriate unit conversion factors works out to be 470 feet. Plotting this result on our intersection plan, we see that this entire area of the median must be kept completely clear of vegetation and other obstructions to ensure that our northbound driver can see far enough to make an informed decision about when it's safe to cross. Now, To cover all the options for just this one northbound vehicle, we'd also need to do a similar calculation for sight distance to the left side and for sight distance necessary to make a right turn and accelerate to 40 miles per hour without causing eastbound vehicles to slow down, and then the same for a left turn. This sort of meticulous attention to detail is absolutely essential for the design of a safe intersection at grade. Element 6, traffic control. The three principal technologies for traffic control are signal lights, signs, and pavement markings. This is a traffic control technology too, but when you encounter this one, you've either stumbled upon some extraordinary situation, perhaps construction, a crash, or a 4th of July parade, or you've encountered a failure of traffic engineering. Under normal circumstances, traffic control systems should work without human augmentation. Traffic control features are designed to ensure the orderly and predictable movement of vehicles by formally assigning the right-of-way to various routes through the intersection. Signs and markings assign the right-of-way permanently, signals do it temporarily on a rotating cycle. In all cases, the engineer's objective is to optimize the inevitable trade-off between delay and the probability of crashes for the conditions the intersection is expected to experience. In the design of traffic signals, the term cycle refers to the total period of time in seconds required for the signal to repeat its programmed green, yellow, red sequence in all directions. The term phase refers to the portion of a cycle in which the right-of-way is uniquely assigned to one or more traffic streams. The simplest signaling configuration is a two-phase light, used at a four-leg intersection. During one phase, the right-of-way is assigned to all north-south traffic, though vehicles making left turns must yield to oncoming traffic. And in the second phase, the same right-of-way is assigned to the east-west traffic stream. Additional phases can be added to control left and right turns, and an all-red phase is sometimes added for pedestrians. As a general rule, adding more phases reduces the number of conflicts, but increases delay. Once the configuration of a signal has been determined, then the timing of each phase must be worked out as well. Pre-timed signals operate according to fixed, pre-programmed cycle times, while actuated signals can be triggered by sensors that detect the presence of vehicles in the appropriate lanes. Actuated systems are far better than pre-timed systems at handling fluctuating traffic flows, and they're also more expensive to install and operate. By the way, the most common type of detector used in actuated systems employs the same principle of electromagnetic induction that we've seen so many times elsewhere in this course. In these systems, an electric coil is embedded in the roadway, and a low-frequency alternating current is passed through it. When a large mass of metal, a vehicle, passes over the coil, the electromagnetic field generated by the coil induces a secondary electromagnetic field in the vehicle itself. This secondary field is detected, in turn, by the coil in the roadway, and the associated controller, typically located in a metal cabinet along the roadside, then changes the phase of the signal accordingly. Because pre-timed signals don't respond to real-time traffic demands, the timing of their phases is particularly important for minimizing delay time. The programmed green time is normally based on traffic volume in the associated direction, with more vehicles per hour warranting a longer green light interval. The yellow interval is timed to ensure that the driver of a vehicle moving at the speed limit has enough response time either to drive through the intersection without speeding up or to stop prior to reaching the white line. Most signals also include a brief period between each change of phase when the lights are red in all directions. This provides an additional buffer for those of you who prefer to accelerate through the yellow light when you really should be stopping. You know who you are. Now, in some urban systems, the signal timing at adjacent intersections along the same road is synchronized to improve the efficiency of traffic flow. In these systems, the start of each phase is timed to occur just as a platoon of vehicles arrives from the previous light. When you encounter one of these synchronized systems, and each light goes green just as you reach it, and you're able to drive completely across town without stopping once, you have experienced traffic engineering at its very best. An old man going a lone highway came at the evening cold and gray to a chasm vast and deep and wide, through which was flowing a sullen tide. The old man crossed in the twilight dim. The sullen stream had no fear for him, but he turned when safe on the other side and built a bridge to span the tide. As Will Allen Dromgoole's early 20th century poem, The Bridge Builder, suggests, there's just something about a bridge. Unlike other forms of civil infrastructure, which tend either to fade into the background or to draw our ire for despoiling the landscape, bridges often inspire respect, sometimes even reverence, and occasionally poetry. And justly so. Who can look upon the Golden Gate Bridge and not be inspired? Who wouldn't feel a sense of awe crossing the Tampa Bay on the Sunshine Skyway Bridge at sunrise? Who could gaze upward at West Virginia's New River Gorge Bridge and not feel her pulse quicken just a bit? Monumental structures like these represent extraordinary triumphs of human industry, ingenuity, and creativity. And yet, iconic as they are, these great spans are entirely unrepresentative of the bridges that have the greatest influence on our everyday lives. According to the Federal Highway Administration, there are over 500,000 bridges in the US. The vast majority of these are not graceful suspension bridges or towering arches, but rather simple highway overpasses and modest spans across small streams. And so, in the spirit of everyday engineering, I'd like to focus today's lecture on these seemingly mundane structures, bridges that, I suggest, can still inspire us, though perhaps in more subtle ways. I won't be discussing the more ambitious structural forms like suspension and cable stay bridges in this course, but if you're interested in learning more about them, I hope you'll check out my Great Courses lecture series, Understanding the World's Greatest Structures. Now, most of the bridges we encounter in our daily lives are simple multi-girder spans like this one. Let's use a computer model to deconstruct this structure and see how it works. The main structural elements in a multi-girder bridge are, of course, the girders. We've already encountered girders in our lectures on residential building construction, and the meaning of the term is exactly the same here. A girder is a main beam that supports other elements of the structural system. In your home, these other elements are the floor joists and subfloor. In a multi-girder bridge, they're the components of this reinforced concrete deck, which we'll examine shortly. Now, as you'll recall, a beam is a structural element that carries load in flexure or bending, like this. In this normal mode of bending, which I'll refer to as concave upward, because the concave side of the bent beam is facing upward. In this normal mode of bending, the beam develops compression on top and tension on the bottom. You can see this quite clearly because these vertical lines on my model, the black ones, get closer together at the top, that's compression, and farther apart at the bottom, that's tension. Furthermore, because the vertical lines remain straight as the beam bends, we can see that the compression and tension vary linearly from top to bottom. Therefore, there must be a horizontal plane running through the middle of the beam, along which there is neither tension nor compression. This plane, which is annotated with a red line on my model, is called the neutral axis. Now, the bridge girders represented in my computer model are made of steel. Concrete girders are also quite common, and we'll examine these in a few minutes. Steel is an ideal material for bridge girders, first because it has equal strength in both tension and compression, and second, because it can be formed into these highly efficient eye-shaped cross-sections. So why are steel girders usually eye-shaped? The answer is that the eye is an inherently efficient shape for carrying loads in flexure. Let's do an experiment. These two beams, one with a square cross-section and one with an eye-shaped cross-section, are made with exactly the same amount of material. Now we can verify this by simply weighing both of them on this very simple balance scale. And because they balance, they weigh the same and therefore are made of the same amount of material. Now let's start with the square cross-section. I'm going to place it on a pair of supports, and when I hang this weight from the center of it, you'll see that it deflects quite noticeably, it bends quite noticeably. In order to gauge how much it bends, I'm going to take this straight edge and place it on the two supports. And looking at the gap between the straight edge and the beam in the center, I think you can see that the amount of deflection is on the order of 1 inch. But when I apply the same weight to our eye-shaped cross-section, and once again hold my straight edge in place, you can see that the amount of deflection in this case with the eye-shaped girder is less than 1/8 of an inch. And indeed, if we loaded both of these beams to failure, we'd see a similar disparity in their flexural strengths. Now, why is this? Well, if we visualize the basic phenomenon of flexure, we can see the answer. Maximum compression occurs at the very top of the beam, and then it decreases linearly to 0 at the neutral axis. Maximum tension occurs at the bottom, and also decreases linearly to 0 at the neutral axis. Clearly, the material closest to the top and bottom of the beam are doing most of the heavy lifting in flexure. Thus, if we concentrate most of the beam's material out here, away from the neutral axis, we can greatly enhance the beam's load-carrying capacity, and that is why eye-shaped beams are eye-shaped. The three components of an eye-shaped beam cross-section are its two horizontal elements, called flanges, and the vertical element, called the web. When this beam bends, the flanges provide almost all of its flexural strength. The web is really just there to hold the flanges in place and to resist several other types of loading that we'll discuss shortly. Theoretically, the farther the flanges are from the neutral axis, the stronger the beam will be. The steel girder that's commonly used in residential construction is called a hot rolled section. It's manufactured by heating a single block of steel and then forming it into shape with huge hydraulically operated rollers. That's why it's called a rolled section. Now, some smaller highway bridges, like this one, use girders made of hot rolled sections. But most bridge girders, like these, are custom fabricated by welding individual steel plates together to form the flanges and web. These structural elements, called plate girders, are generally more efficient than hot rolled sections because they can be individually tailored to the requirements of a given structure. Plate girders can also be made much larger than even the largest hot rolled beams. Thus, plate girder bridges are routinely built with spans exceeding 300 feet, while hot rolled beams are only suitable for spans about 1/3 that length. But as we've seen before in this course, the quest to optimize a technology with respect to one performance criterion often creates problems with respect to other criteria. In the case of the plate girder, flexural strength and stiffness is enhanced by making the cross-section taller and by using proportionately more material in the flanges. But as this cross-section gets taller and the web gets thinner, all sorts of new problems crop up. The first is a phenomenon that we first encountered in wooden floor joists in a platform-framed residential floor system. The failure mode called lateral torsional buckling. Now, recall that in general terms, buckling is an instability failure that occurs when a compressed structural element kicks out sideways, like this. Now, in bending, an eye-shaped beam has its top flange in compression as well. So the top flange is susceptible to that same sort of buckling failure. When this happens, the top flange kicks out sideways, like this, resulting in a twisting or torsional failure of the beam. Here it is again. And tall I-shaped girders are particularly susceptible to this failure mode because they're very flexible in torsion. Note how easy it is for me to twist this model I girder. Now, the only practical way to prevent this failure mode in an I-shaped girder is to brace the top flange laterally so it can't buckle sideways. Again, just as we saw with a lateral torsional buckling in wooden floor joists. But what can we use to brace it? Why, another girder, of course. And herein lies the principal reason why I-girder bridges must have at least two girders. Each girder must be braced, at least in part, by its neighbor. In most modern highway bridges, this bracing function is accomplished in two ways. First, the girders are interconnected with these transverse frames called diaphragms, which function as miniature trusses to prevent the girders from twisting. Here's a set of actual diaphragms awaiting installation on a bridge. And by the way, these elements serve another important structural function that we'll discuss later. Second, the top flanges of the girders are usually rigidly connected to the concrete deck. Thus, just as wooden floor joists are strengthened against lateral torsional buckling by the subfloor panels, so steel bridge girders are strengthened by the concrete deck. The rigid connection between the girder and the deck is provided by these vertical steel posts called shear studs, which are welded to the girder's top flange. When the concrete is poured, it completely encases the studs and then hardens, creating a rigid mechanical connection. And not only does this connection prevent lateral torsional buckling, it also significantly increases the girder's flexural strength by turning the entire concrete deck into a sort of extension of the girder's top flanges. This is called composite construction, and it's particularly common on long-span girder bridges where the additional fabrication cost associated with welding all those shear studs onto the girder flanges produces its greatest payoff. These bridge girders don't yet have shear studs installed, but if we look very closely, we can see a clear indicator that they've been designed as composite girders. Can you see it? Notice that their top flanges are just a bit thinner and a bit narrower than their bottom flanges, indicating that the designer has planned for the additional contribution that the composite concrete deck will make to the strength of the top flange once the studs and concrete have been added. If the girder weren't intended to be composite, both flanges would be exactly the same size. Now, the other problems associated with tall I-shaped girders are all related to the thinness of the web. And as you've probably guessed, the best way to understand the underlying structural phenomena is with a model. Now, the web of this model I-girder is made of thin sheet metal. And when I take that girder and place it on my supports, and then load it, you're going to see that the concentrated reaction force out at the supports causes the web itself to buckle vertically at its ends, like this. In actual girders, this issue is addressed by adding elements called web stiffeners. They're vertical steel plates welded to the web at all supports, as you can see here. And so, I've added web stiffeners to this model. And once again, I'll place it on my supports and load it. But now a new problem arises. Notice that as I apply load, the entire web of the girder seems to buckle diagonally between the web stiffener and midspan where I'm applying the load. The underlying cause of this issue is a phenomenon called shear or shearing. This phenomenon is quite complex, but at the most fundamental level, it's the tendency of the girder web to distort from a rectangular shape to a parallelogram shape on either side of the applied load, as shown in this diagram. Note that when I apply a shearing force to this book, we see exactly the same effect. The problem of shearing in girder webs can be addressed in either of two ways. The first, which is most common on older bridges, is to add web stiffeners all along the length of the girder, as you can see in this photo. And this approach works quite well, as you can see in my model. Here I've added web stiffeners along the length of the girder, and when I apply the same loading that I did before, you can see that there is still a tendency of the web to buckle, but now that buckling is contained by the additional vertical web stiffeners, and therefore the girder is significantly strengthened. The problem with web stiffeners is that they're expensive to fabricate and install, often offsetting the cost savings that might have been gained from using a thinner web. So today, the more common solution is simply to use a somewhat thicker web, sometimes augmented by just a few stiffeners placed on the inside of the girder web, where they won't adversely affect the aesthetics of the bridge. These internal stiffeners can also serve as mounting points for the diaphragms, as you can see in my computer model, and in this actual bridge. Now, by the way, in the foreground of this photo, you can also see additional diagonal bracing interconnecting the bottom flanges of two adjacent girders. This is called wind bracing, and as the name suggests, its purpose is to prevent the girder from bending sideways in response to lateral wind pressure exerted on the girder webs. After today's lecture, I hope you'll start looking more closely at everyday bridges. And when you do, you'll probably notice that many older bridges, like this one, use only two girders, which typically extend above the level of the roadway like this. But virtually all newer bridges use more than two girders. Why is this? Well, there are several reasons, but the most important is that using a larger number of smaller girders provides improved safety through structural redundancy. If one girder of a two-girder bridge fails, the structure will almost certainly collapse. If one girder of an 8-girder bridge fails, the structure will almost certainly survive, saving lives and ultimately allowing for repair rather than replacement. But why would a girder fail anyway? Isn't it the bridge engineer's job to ensure that this doesn't happen? Well, certainly. Bridge engineers take every reasonable precaution to avoid failure, but the ugly truth is that a zero probability of failure is impossible to achieve. Sometimes natural disasters load structures in ways that no engineer could anticipate. Sometimes the drivers of trucks and buses don't pay attention to overhead clearance restrictions. But the most important reason for structural redundancy is fatigue, the progressive accumulation of damage in metals subjected to repetitive loading. In a steel bridge girder, fatigue begins with a microscopic defect or crack in a web or flange, or more likely at a welded connection, where concentrations of stress tend to occur. If this portion of the girder is repetitively loaded in tension, each cycle of load extends the crack by a minute amount. Over time, as this process continues, the extension of the crack gets progressively larger as the concentration of stress at the tip of the crack gets higher. At some point, typically after a few 100,000 load cycles or more, the crack can reach a critical length, at which point a sudden, catastrophic fracture of the entire girder occurs. Now, fatigue isn't a significant concern in steel-framed buildings, because buildings typically don't experience enough load cycles for fatigue cracks to approach their critical length. But major bridges are routinely crossed by thousands of heavy trucks per day, perhaps 1 million per year, and each truck produces a substantial load cycle that can contribute to fatigue damage. Thus, fatigue is an overriding concern in steel bridge design. Bridge engineers address this concern in 3 ways. First, by avoiding the specific types of welded connection details that are most prone to fatigue-related problems. Second, through rigorous quality control in the fabrication and assembly of bridge components, to include such measures as X-raying welds to ensure that they have no internal defects. And third, by providing structural redundancy. This approach is often called belt and suspenders engineering. Take every reasonable precaution to prevent failure, and then provide a backup system just in case a failure happens anyway. Remember Kipling's poem, The Sons of Martha, from Lecture 1. They do not preach that their God will rouse them a little before the nuts work loose. Now, having looked very closely at steel girders in a multi-girder bridge, let's examine the concrete alternative to steel. As we've seen, the most fundamental characteristic of concrete as a structural material is that it's very strong in compression, but very weak in tension. And because beams experience comparable magnitudes of tension and compression, the only practical way to use concrete in flexure is to reinforce the portion of the beam that's in tension. In most structures, this reinforcement takes the form of steel reinforcing bars, like these, which are positioned in the concrete forms before the concrete is poured. After the concrete is hardened, the steel and concrete are locked together into a single composite structural entity. Conventional reinforced concrete was used extensively for highway bridges in the early and mid-20th century, though today it's considered to be obsolete and has been largely replaced by a far superior technology. Let's see why. I'm going to use this stack of wooden blocks to represent a concrete beam. Now, this might seem like a stretch, but it's actually a reasonable representation because, like concrete, the stack is very strong in compression. As long as I push inward, it holds together, but it has essentially no strength and tension. Watch what happens when I attempt to use it as a beam. Just falls apart. Because of this lack of tensile strength, which is so critical for flexural behavior, I'm going to reinforce the bottom portion of this girder by inserting this steel reinforcing bar. And then I'll use a washer and a nut on each end just to hold it in place, simulating the effect of the concrete providing a rigid bond between the steel and the concrete beam that surrounds it. Now I'm going to set up a set of supports for our girder. And I will place the beam on the supports. Now you see it does carry its own weight reasonably well, but I'm also going to apply an additional superimposed loading in the form of these 3 bricks. And what you can see is that while the girder carries this load successfully, it cracks noticeably all along its bottom surface as a result of the tensile loading that naturally occurs in the bottom of any beam in flexure. Now, it's important to recognize that this is absolutely normal behavior for a reinforced concrete beam. For steel to provide the necessary tension reinforcement in the bottom of the beam, the steel has got to stretch. And the amount of stretch necessary to mobilize even a modest portion of the steel's own strength is far beyond the threshold at which concrete cracks. Thus, the presence of moderate cracking in the bottom of a reinforced concrete beam actually tells us that the steel reinforcement is doing its job. But, normal as it might be, cracking causes 2 critical problems. First, it leads to significantly increased deflection or sagging of the beam, and I think you can see that deflection in my model. And second, these cracks can expose the steel reinforcement to moisture, which leads to corrosion and potentially to a catastrophic loss of tensile strength. In building structures, where reinforced concrete is used quite often today, these issues generally aren't problematic because span lengths can be kept relatively short to control deflections, and the building envelope can protect the beams from exposure to moisture. But in bridges, the need for longer spans and for constant exposure to the elements have effectively rendered reinforced concrete obsolete and stimulated the development of a new technology called pre-stressed concrete. The concept of pre-stressed concrete is actually well over a century old, but the technology didn't really catch on for bridges until the 1950s. Since then, its use has grown steadily, even as improved materials and design methods have significantly improved its effectiveness and efficiency. For the everyday bridges that we're focusing on today, there are 2 principal methods of fabricating pre-stressed concrete girders. Both occur in a controlled factory environment, not out on the construction site. In the first method, a series of extremely high-strength steel wires, called tendons, are strung between 2 anchorages mounted on the shop floor. Hydraulic jacks are then used to stretch the tendons almost to their breaking point. Next, the concrete beam is cast around the stretched tendons. After a few days, the concrete hardens enough to form a strong bond with the tendons. The reusable forms are removed, the ends of the tendons are cut free, and the tension in the tendons is transferred to the concrete as compression. The mechanism for this transfer of force is the bond between the steel tendons and the surrounding concrete. This technique is called pre-tensioning because the tendons are stretched before the concrete is cast. In the second method, a hollow duct containing an unloaded tendon is cast right into the concrete girder. And then after the concrete has cured, the tendons are anchored at one end with wedges, tensioned with hydraulic jacks from the opposite end, and then anchored at that end as well. This process is called post-tensioning. Now, in either case, the effect on the concrete beam is essentially the same. And we can actually simulate this effect on my model by tightening this end of the steel rod that I've already embedded in the concrete. So I'm going to tighten this down first as much as I can by hand. And then I'm going to clamp off the back end and use my wrench to finish the job. In this manner, I am effectively post-tensioning the beam. Now note that in doing so, I've added tension to the rod, but the rod is itself compressing the bottom of the beam. And the beam actually arches upward slightly as a result. So now, with my girder on its structural supports, I can apply the same load that I applied previously to our reinforced concrete beam. And in this instance, you can see quite clearly that the effect of the pre-stressing has been to eliminate both the downward deflection of the beam and the cracking all along the bottom surface of the beam. And so you can see that in pre-stressed concrete, the effect of pre-stressing is to apply compressive stresses in the region of the beam that normally experiences tension. In a material like concrete that's strong in compression and very weak in tension, this offsetting of tension greatly improves structural performance. Here are several pre-stressed concrete beams awaiting installation on a bridge, and here they are in a completed multi-girder bridge structure. Note that these beams are I-shaped, meaning that they can achieve the same sort of structural efficiency we saw in steel girders. Yet because of their more robust proportions, these girders are not susceptible to the lateral torsional buckling problem or web buckling challenges that we saw in steel girders. For these reasons, today, pre-stressed concrete has become highly competitive with steel for short and medium span bridges. And so, when you're out on your next bridge sightseeing road trips, a pastime I highly recommend, you might very well see both types in comparable numbers. Now let's look beyond the girders at the structural system that's common to both steel and pre-stressed concrete multi-girder bridges, starting with the deck. A few decades ago, this bridge deck would have been constructed by first erecting temporary wooden formwork between the girders like this, and then adding these two layers of steel reinforcing bars, and then pouring concrete over the entire assembly. Two layers of reinforcement are needed because the critical loading for a bridge deck occurs when a heavy truck's wheel loads happen to be centered between the girders, like this. Note that under this loading, the bridge bends in double curvature, and here, where it's concave upward, tension occurs at the bottom, but here, where it's concave downward, tension occurs at the top. Therefore, two layers of reinforcement are needed. Well, that was then, but this is now. Today, this deck can be built at considerably lower cost and much faster by using this corrugated steel decking instead of temporary formwork. The decking holds the wet concrete just as formwork does, but it also provides permanent tension reinforcement at the bottom of the deck, and thus replaces the entire lower layer of reinforcing bars. When you drive beneath an overpass bridge and look up, you can usually see the product of this very ingenious system, as you can see in this photo. Now, when I introduced this structure at the start of today's lecture, I called it a simple multi-girder bridge. In this context, the term simple has a very specific meaning. It refers to the manner in which each girder is supported at its ends. In engineering textbooks, a simply supported beam is depicted symbolically, as you see in this diagram, with something called a pin support at one end and a roller support at the other. The pin prevents the end of the beam from moving in both the vertical and horizontal directions. The horizontal restraint is important here because vehicle braking forces can impart huge horizontal loads on a bridge. The roller support at the opposite end of the beam supports that beam only from below, while allowing unrestrained horizontal movement. This lack of horizontal restraint is also important because it allows for thermal expansion and contraction of the beam. Between the extreme temperatures of a cold winter night and a hot summer day, a 100-foot-long steel girder expands about 1 inch. And if the supports don't accommodate this movement, the resulting internal stresses could be large enough to cause serious structural damage. Now, back in the day, bridge engineers designed pin and roller supports that look astonishingly similar to their symbolic representations in textbooks. Here are a few examples. But today, smaller bridges typically use bearing pads like these, which are simpler and less expensive and actually perform better because they don't have any moving parts that can corrode and freeze up over time. Modern bridge bearing pads are typically made of synthetic rubber or polymer sandwiched between two steel plates. The flexible core accommodates the girder's lateral movement by shearing back and forth, just like my book. These bearings are supported on concrete abutments, which serve two complementary functions. First, they provide the bridge's structural foundation, transmitting its weight and all of its applied loads down into the soil below. Second, they serve as retaining walls, holding back the earth embankments on which the roadway is built. In multi-girder highway bridges, the principal alternative to simple supports is the continuously supported span. And here's how it works. In addition to pin and roller supports out at its ends, this configuration includes one or more intermediate supports, which are usually mounted on concrete piers like this one in the center of my model. As the name suggests, a continuously supported girder extends continuously from one abutment across the intermediate pier to the other abutment without any breaks in continuity. This configuration is somewhat more structurally efficient than a simply supported span because that single girder bends in double curvature, much like the bridge deck we examined earlier. Note, concave upward bending out on the ends of the span, concave downward bending over the intermediate support. For this reason, and because a single intermediate pier can be positioned very conveniently in the median of a divided highway, two-span continuously supported multi-girder bridges are used quite commonly for highway overpasses like this one. The everyday highway overpass bridge is a thoughtfully engineered system that serves as an essential component of our transportation infrastructure. When we notice these structures at all, we tend to think of them as unremarkable or perhaps even ugly. Yet many have a simple elegance that clearly reflects a designer's effort to provide us with something beyond bare utility, perhaps even something worth admiring. Back at the start of this lecture, I read a few lines from the beginning of Will Allen Dromgoole's poem, The Bridge Builder. What better way to conclude than with the final few lines? There followed after me today a youth whose feet must pass this way. The chasm that has been as naught to me, to that fair-haired youth might a pitfall be. He too must cross in the twilight dim. Good friend, I'm building this bridge for him. Large or small, elegant or humble, there really is something about a bridge.